Morning everybody, happy Monday. Hopefully you're all doing good out there. Kind of a rainy day. Nice day to be doing some chemistry inside. If we can start with some green check marks, and I will make sure we're all doing okay. And then we'll continue on from where we left off last day. Good. Everyone's checking in. So we're going to continue on with the chemistry stuff. We spent 2 days last week. We only had like 2 hours and a bit of class, so we didn't get a whole lot of headway made through the material. We're going to pick it up a little bit today and the next time we meet, and hopefully we'll get some more stuff out of the way. Hopefully some of the stuff today we're doing will be new. Some of you mentioned that you'd seen Bohr models and you'd done some of the previous things we'd already been doing, so we'll just continue on from there. I didn't leave you guys with any work to do, and so we're just kind of continuing on from where we left off. So the midterm's coming up in a couple weeks. See, Abby, you're asking about it. So the midterm will be on chapters 1, 2, 3, and 4, and 10. So the biology unit, chapter 10 was the earth science, and then we're going to hopefully get done unit 4 this week. So that'll kind of be it. 1, 2, 3, 4, and 10. Nothing will have any more of a focus than anything else. I'm going to try to break it up fairly evenly amongst those 5 chapters. And when we get to the end of this week, I'll be able to tell you for sure what's going to be covered. Just depends on how far we get and how fast we can get through this stuff. So we do have 2.5 hours today, which is a long time, but we do need to get through some of this material. I want to make sure you guys are on it. So we're going to start with Lewis diagrams, and I think that's where we're at. I'm just going to kind of fly through the notes here. We've gone through all this twice now. I talked about ions and atoms, and we used some of those square brackets. Forming compounds we talked a little bit about. I spent all of last day, a whole hour, describing how to form compounds with these things, and it's kind of a foundational sort of thing in the material we're going to cover today and how we're going to move forward. So you're probably thinking, Mr. Borden, just get on with it. There's not that much in the notes about this stuff or anything like that, but it's kind of important to know why, we have all these charges on our periodic table. Where do those charges come from? Why do the atoms decide to gain or lose electrons? If we don't understand that, everything moving forward is really sort of a difficult concept to master. But if you can kind of understand the how and the why behind it, then you, moving forward, should have a really good understanding and you should be doing okay. So we started to talk a little bit about covalent bonds. In this slide here, it was just mentioned at the bottom. We're going to talk about that a little bit later today. But the ionic bonds, we're talking about atoms getting rid of electrons and then some atoms receiving electrons. If you're gaining electrons, you get a negative charge. If you're getting rid of electrons, you're going to have a positive charge. So we tried sodium and chlorine. We did another example, which was much more difficult, and that's kind of where I left. So today we're going to talk about covalent bonds, and we'll spend just a little teensy amount of time on these things, and then we'll just kind of forget about them for a while, and then we'll actually come back to them later. So hopefully at the end of the class today, we'll see these things again. But covalent bonds are different than ionic bonds. Ionic bonds form between ions. Ionic ions they form. When electrons are transferred from one atom to the other and they're shared, we call them covalent. When they're transferred, we call them ionic. So oxygen, we're breathing oxygen right now. Oxygen is called a diatomic atom. So if you get 2 oxygen atoms floating around in space, they come really close together. What's going to happen is the outer shell of oxygen, you can see here, has 7 electrons in it. And the other oxygen here also has 7. So they're 1 electron away from having a full outer shell. But instead of having an electron transferred from one to the other, what they do is they just end up sharing electrons. So if you're this oxygen here, you have these 2 electrons, 1, 2, 3, 4, 5, 6, and then it's sharing these two over here, so 7, 8. And then same deal over on this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. And that actually is a double bond. So this is one example here, just above my head. The oxygens share electrons to fill their outer shells. The other example down below is water. Hydrogen has 1 valence electron, and oxygen has 2, 4, 5, 6. So this hydrogen is going to share this electron here. This hydrogen is going to share this electron here. And they're sharing pairs of electrons. And when they do that, they form really stable compounds. Now, the key, the most important thing to tell the difference between an ionic compound and a covalent compound is ionic compounds have a metal, so something from the left side of the periodic table, with a non-metal, which is something from the right side of the periodic table. When we talk about covalent bonds, they're 2 non-metals. And in this case, hydrogen's one of these goofy ones that behaves like both a metal and a non-metal. So that's just covalent bonds, really briefly described and explained. We'll come back to it, we'll spend more time on it, but for now that's basically enough to keep you going. Let's look at one example using the Bohr models. So hydrogen and fluorine. These are 2 nonmetals. In this case, hydrogen is behaving like a nonmetal. So if you have like I asked you to have just a scrap piece of paper out, you want to just try it on your own. I'm going to jump over to OneNote and try this. So hydrogen is 1 proton, 0 neutrons, and it has 1 electron for its 1 proton. So that's hydrogen. And then we have fluorine. And fluorine is element number 9. Leave some space here. So it has 9 protons. It has a mass of 19, so it has 10 neutrons. Hopefully you're okay with me coming up with those. So the first shell will have 2, and then the second shell will have 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So instead of electrons being transferred from the hydrogen to the fluorine or the fluorine to the hydrogen, what's going to happen here is the electrons are going to be shared. The hydrogen's behaving as a nonmetal and the fluorine is a nonmetal. So if I had another hydrogen down here, and that hydrogen had, did I get that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. I did get it right. I don't need that one. So what's going to happen is this electron here and this electron here, they're going to kind of share. So hydrogen has room for 2 electrons in its outer shell to fill it. Fluorine has room for 8, but it only has 7. So what's going to happen is these 2 things are going to join together. So instead of electrons being transferred from one to the other, they're just going to share them. Draw my little hydrogen over here. All right. I guess I draw it a little closer. 1 proton, 0 neutrons. Makes more sense. All right, so there's that 1 electron from hydrogen. There was that 1 from fluorine. Fluorine also has another 7 in that shell, 2 in this shell. Now the way to think of this is if we're looking at hydrogen here, if I look at hydrogen, how many electrons does it have? Well, it has 1, 2. 1 here and another 1 here. Perfect. It's happy. It has a full outer shell. What about fluorine? If I do the same thing with fluorine, draw this outer shell again. If I look at fluorine's outer shell, this green circle, well, it has 1, 2, 3, 4, 5, 6, 7, 8. So fluorine's happy as well. So instead of electrons being transferred from one to the other and then becoming charged and then the charges sticking those things together, in covalent compounds, the electrons are just shared. So they don't get transferred, they just share them. And there's a way we can draw this in a second. We'll look at Lewis diagrams, and hopefully that'll make a little bit more sense. All right, I know I was kind of rushing through that. If you didn't really grasp it, it's okay. We'll talk about it again in a second. So this is where we're at, Lewis diagrams. Now, we've done Bohr models, and Bohr models are great. They show protons and neutrons, and they show the electrons in the outer shell and the inner shells. Lewis diagrams, you can kind of think of them as lazy Lewis diagrams, I guess. So Lewis diagrams are really easy way of showing the valence electrons, only the outermost electrons. Now, the reason we only care about the outer electrons are because those are the ones that are involved in bonding. So we're not really concerned about the inner shells because they don't have anything to do with bonding. Only the outside electrons have to do with bonding. So with the Bohr model in the middle, we drew protons and neutrons, but for Lewis diagrams, we just write the symbol for the element. So hydrogen's H, lithium's Li, you get the idea. Instead of showing all of the shells, we just show the outermost shell. And it makes life a lot easier. Now, one of the key ideas for Lewis diagrams to make your life so much easier is that if you're in the first column in the periodic table, you have 1 electron in your outer shell. So you can see that everything in the first column here has 1 dot. Hydrogen, 1 dot. Lithium, 1 dot. Sodium, 1 dot. Everything in the second column has 2 dots. Third column, or 13th column, I should say, is 3. 14th is 4, 15th is 5, 16th 6, 17 7, and 18 is 8, with the exception of helium up at the top because it can only hold 2 because it's in the first period. So Lewis diagrams are just an easy way of doing everything we've just done. Makes it a lot faster. Instead of drawing all the circles and things like that, you just draw the symbol and then put the outermost shell, the outermost dots. So similar to Bohr, but just a little bit easier. We can represent ions the same way as we did with the Bohr model. So if we have a full outer shell, you draw the brackets, the dots, and then the charge. One thing that gets a little bit tricky is that when you have something like sodium or magnesium or any metal, and the metals are all going to lose their outer electrons. So you'll notice for sodium and magnesium, the first 2 examples here, there's no dots. Does that mean its outer shell or it doesn't have any electrons? No, it just means its outer shell is empty. It's gotten rid of all of the electrons in its outer shell. So we don't indicate any dots with the metals. The nonmetals, when we draw ions, are always going to have full shells because they'll always try to gain a full outer shell. So, yeah, Abby, hydrogen is the exact same process. If hydrogen's acting like a metal, you would have hydrogen, square brackets, and then a charge of +1 with no dots. If you have hydrogen behaving like a non-metal on the other side of the periodic table, you'd have H, and then you'd have 2 dots and a charge of -1. So it's the same deal for hydrogen. Helium too, because helium only has 2 electrons in that outer shell, we could draw helium with just the 2 dots, and then it's happy that way. So it's like a Bohr model, but it's just a lot easier. So this is like a little gift from the science gods. So I'm not going to spend a ton of time talking about Lewis dot ionic compounds because they're exactly the same as the Bohr model, except we just have the symbol and then the outer shells. So it's pretty straightforward. Covalent gets a little bit different. We just talked about covalent, and I just did an example of hydrogen and fluorine. So this is the exact same example I just did, but with Lewis structures now. So hydrogen's H has its 1 electron. Fluorine has 7, so F with its 7 electrons. We talked about hydrogen and fluorine sharing outer electrons. And instead of drawing these 2 dots here, we represent a pair of shared electrons with a line. So this line is actually 2 electrons. I clicked. Hard. There we go. So The lines, when you see Lewis structures and sharing electrons, the lines indicate 2 electrons. That's kind of the only sort of trick with the covalent compounds, is that a line is 2 electrons. If you're fluorine, you have the 2 at the top here, you have the 2 on the side, and then the 2 on the bottom, and then the line is an additional 2, so that's 8. If you're hydrogen, you just have the line, which is 2, and that's all you need to fill your shell, so you're full and happy there. So that is kind of the difference between ionic and covalent with the Lewis dot structures. We did an example of oxygen with the Bohr model, or I guess there was like a little diagram of it. This is the same example here. Notice oxygen has the 2 dots at the top, 2 dots at the bottom, and then if you looked at the line, represents 2 and another line is 4. So 1, 2, 3, 4, 5, 6, 7, 8. And then you have the other oxygen, 1, 2, 3, 4, the line is 5, 6, the other line is 7, 8. The electrons that are hanging out by themselves up above oxygen, these are called lone pairs, and then the lines that are sharing electrons are called bonding electrons or bonding pairs. The term lone pair comes up a fair amount. I don't know why they love it so much on the final exam, but lone pair is something that they'll definitely usually be a question on lone pairs. So it's just one of those kind of vocab things that you need to know about. So that's that set of notes. I'm just going to jump to the learning guide and we can just make sure we're on the right track with the information in there. All right, so I asked you to skip number 10. Which type of atom can form a covalent bond and which type can only form an ionic bond? Remember, one of the important features about a covalent bond is that it's 2 nonmetals. So I'll just answer this for you. So I'm in a good mood. Ionic has at least 1 metal. Covalent is 2 nonmetals. So if you have an ionic compound, there has to be a metal in it. If you don't have any metals, then you don't have an ionic compound. And remember, on your periodic table, you have this staircase that kind of separates the blue in the middle from the brown up here. That staircase separates the metals from the nonmetals. There's far fewer nonmetals up in this corner here. So there you go. Metals, nonmetals. You can draw Bohr models for ions. You can draw Lewis structures now. You should be okay with all of those. Group number, yep. Draw Lewis structure for sodium oxide and nitrogen. You should be okay there. And now we're on to 4.2. So there's a few practice questions on Lewis structures that you guys should do for next class. I'm just going to keep going on to 4.2 in the notes. And then if you guys have any questions next day about the Lewis structure table that's in the course here, then you can ask those next day. So what we're going to do is we're just going to mosey on. Does anybody have any questions about any of that stuff in general? Anything to do with ionic, covalent, Bohr models, Lewis structures at all? Anything? Going once, going twice? All right. The next section. Now, I'm going to apologize in advance that aside from the first slide here, names and formulas of compounds, the material in this section isn't really presented in a very visually appealing way. I didn't put in many pictures, and there's not a lot of pictures and things to include, unfortunately. It's just kind of like getting back to math, where you just have some rules and you got to kind of practice those rules. Were we supposed to do number 12 in the first set of questions? This on page 12, Taylor? Number 12 on page 12? Yeah. I'm thinking that's what we're going to do for next day for sure. There'll be some additional stuff as well. Okay, yep, you're good. We'll be practice this week. We used to have for math, get ready for the test at school, I mean. Will there be like a Wednesday study sort of session? Like we had before? I didn't plan on it, but maybe we can schedule one next week. Maybe we can schedule a couple next week if there's need or if lots of people feel like they want to come in and get some extra help on this stuff. We could maybe do Wednesday next week. I don't think I have anything going on Wednesday next week, Wednesday afternoon, for sure. And then I'll see if there's enough demand for another day. Just kind of informally, would anybody be interested in coming in for extra help on Wednesday? Just kind of like a wave or a check mark or a, sure, Mr. Borden. Or I got my brain wrapped around this stuff, I think we'll be okay. So Abby for sure, that's fine. As long as one of you wants to come in, we can definitely make time. Cool. After today's lesson, you might change your mind and more of you might want to come in because we're going to get into some new things here. All right. The ionic versus covalent the differences between these things we're going to continue. And today we're going to talk about naming these compounds. And some of you before, when we were looking at some of the compounds, were like, Mr. Borden, isn't that called sodium chloride instead of sodium chlorine? And things like that. And you'd obviously seen some questions like these before. So we're going to spend a lot of time on them, hopefully, and make sure you guys have a really good understanding of this. Now, the really, really important thing for this section is that, again, if you don't understand how to name these things, the next section's on balancing, you won't understand that. So you gotta just make sure you wrap your head around this. And if you're having issues or you're running into problems or you don't just get something, make sure you ask. Because if you're lost here, you're gonna be lost in the next section. And it's kind of not a good thing for the rest of chemistry. So ionic compounds, we've talked about this already. It's made up of metals and nonmetals. You have a positive ion, which is your metal. You have a negative ion, which is your nonmetal. The positives and negatives attract each other, they stick together. The electrons actually get transferred from one atom to the other. And all of our all of our ionic compounds will form crystalline structures. So the little blue and green guy, or purple and green guy here, this is how all ionic compounds will look. They'll all have this crystalline structure. That if you've ever looked at like a salt crystal under a microscope or like magnifying glass, you can see that it kind of looks like a crystal, and they are in fact crystals. So there you go. Ionic compounds form these nice crystalline structures. Covalent compounds don't generally form these types of structures. The molecules just they don't form these nice lattices and rigid structures. They just kind of clump together, and you end up with not the nice crystals that the ionic compounds will have. So that is covalent. Covalent molecules share electrons. And one thing that's kind of interesting is if you think about the periodic table. So if I'm talking about an ionic compound, I'm taking something from the metal side and I'm combining it with something from the non-metal side. And you think, wow, there's a ton of metals, very few non-metals over here. You could probably make like tons and tons of different sort of compounds. And then to think that the covalent molecules are just non-metals bonding together, sharing electrons, you'd think, well, there's probably only very few sort of options when you come to sharing amongst this, there's only a few elements here to share with. But it turns out that there's way more covalent molecules than there are ionic. Ionic, you're limited. You have to take a metal and you take a non-metal. There's only so many combinations of metals and non-metals you can come up with. One metal, one non-metal. With covalent, you end up with things sharing all sorts of different combinations, and you run into like way larger variety of molecules. So it doesn't really make sense, but it is. This is kind of the heart of what we're going to do today, naming ionic compounds. And some of you have done this already last year, and it's It's pretty straightforward. The rules are pretty basic. Taylor, is there ever a metal and a metal together? No, metals won't bond with metals because metals always want to get rid of electrons. And if I'm trying to get rid of electrons or you're trying to get rid of electrons, we can't really be happy together because we're both trying to get rid of electrons. So because the nonmetals want to gain those electrons, they can, combine together. So ionic compounds, positive charge, negative charge, they balance out. And the ratio is always written in reduced form. Let's just skip these examples because I want to get moving here. All right, let's just look at this one. This is the one under your notes, and then we can go back if we need to, or I'll introduce some other examples. If I asked you to form an ionic compound between magnesium and phosphide, what you need to do is find these two elements on your periodic table. So magnesium's a metal, so we need to find it on the metal side. And then phosphorus is a nonmetal, we need to find that on the nonmetal side. So we find it, and the idea here is we need to know the charge that these things form. So I find magnesium, element number 12 on the periodic table, has a charge of +2. It's in the second column, so it has a charge of +2. It wants to get rid of 2 electrons. Phosphorus is in column 13, has a charge, sorry, did I get that right? I did not get that right. Phosphorus is in column 15, has 5 electrons in its valence shell. It wants to gain 3, so it has a charge of -3. You don't really need to know that it wants to gain or lose. If you can just look it up, phosphorus has a charge of -3, magnesium's +2. You're off to the races. So we spent some time drawing Bohr models for these things, and we looked at how they're going to combine based on magnesium wanting to get rid of 2, phosphorus wanting to gain 3. Well, if magnesium gives 2 to phosphorus, phosphorus still needs 1 more. So there's a couple different ways we can do this without drawing the Bohr diagrams. You're free to draw a Bohr diagram or a Lewis dot structure here, but there's some easier ways. So you run into 2 options. Option number A, we call the crisscross method. And this will work 90% of the time, but you run into a few problems with it, which we'll talk about. So what you can do is if you draw magnesium with a +2 and you draw phosphorus with a -3, if you take the charges of those things and cross them, so the 2 that's next to the magnesium goes down next to the phosphorus and the 3 that's next to the phosphorus goes down next to the magnesium, you end up with Mg3P2, like you can see down here. So that's one way to think about it. The other way to think about it is, okay, magnesium and phosphorus, my charges have to balance out. So if magnesium has a charge of +2 and phosphorus has a charge of -3, what's common between 2 and 3? Well, the lowest common multiple of those things is 6. So how am I going to get a charge of +6 with magnesium? And how am I going to get a charge of -6 with phosphorus? So if I have 3 magnesiums, that's 2, 2, and 2, that gives me +6. If I have 2 phosphorus, that gives me -3, -3, that's -6. So the charges balance out. And they always have to balance out. So we always put the subscripts, these are called subscripts, these little numbers, at the bottom of the thing. So it always goes behind the thing it's talking about. So the 3 is dealing with the magnesium and the 2 is dealing with the phosphorus. So that is how we form compounds. Let's do another one, calcium and oxygen. See if you can figure out what this compound is going to look like. You can think about taking those charges and crossing them down, call it the crisscross method if you will, or you can think about how are these charges going to balance out? If you have +2 and you have -2, do we need more than 1 of anything or do they just balance as it is? What do we think? What is this thing going to look like? This is where we run into problems using the crisscross method as opposed to just thinking about the charges balancing. And maybe somebody's going to see that this thing kind of runs into problems. So Taylor's saying Ca2O2. Metal first, calcium with the 2 next to it, then the oxygen with the 2 next to it. I like that. Ca2O2. Does anybody have any different answer? Is there something else going on here? Taylor, I walked you into a trap. I walked you into the slaughterhouse and you didn't make it out. So if you take the 2's and you cross them, that works. There's nothing wrong with that. But there's one problem with it. You're running into a problem here, Taylor, where you haven't reduced it into lowest terms. So if you have 2 calciums and 2 oxygens, is there a simpler way to do that? If you just had CaO, just calcium and oxygen, and you didn't have any numbers behind them, if there's no number, we just assume it to be 1, kind of like we did in math with exponents. So do I really need 2 calciums for 2 oxygens? If I have 2 calciums, each calcium's plus 2, that's plus 4. If I have 2 oxygens, that's 2 minus 2, that's minus 4. Is there a simpler way to do it? Well, if I just had a Ca, which is plus 2, and an O, which is minus 2, I combine those together, then the charges are balanced, and that's what I want to do. So the one sort of thing that was written on this slide back here that I didn't highlight your attention to very well is this last point here. The ratio is always written in reduced form. So if you have a 2 and a 2, you need to reduce those, kind of like reducing fractions in math. If you have a 4 and a 2, you can reduce that to a 2 and a 1, and we don't write the 1 in. So you run into kind of problems with some of these things, and it's not meant to be difficult, but it just kind of, you run into problems. If you're just crossing your charges, if there's a common factor, like a 2 or a 3 in there, you can reduce it to lowest form. That's really important. So there are literally thousands of different combinations of these things, and they can get really tricky. So the examples that are in the learning guide, I don't really feel are enough to get you guys through this with a good sort of understanding. Yeah, Taylor, for now, yeah. I say, yeah, it'll always be that way. But when we talk about covalence in a little bit here, things get a little trickier. I don't think we'll get to covalence today, but we may. So for now, yes. Reduce them always, and then you'll be okay. The really great thing about naming ionic compounds is that you name the metal first, you name the nonmetal, and then you just change the ending of the nonmetal to "ide." So we just did calcium and oxygen, so that would be called calcium oxide. If you do magnesium and oxygen, it'd be magnesium oxide. So we just changed the nonmetal ending to "ide." That's it. That names all ionic compounds. So we'll look at some exceptions to that, but generally speaking, you name the metal, you name the nonmetal, you change the nonmetal ending to "ide." I'm gonna go back here. There was some examples that I didn't do that are not in your notes that I kind of want to do, just so we're on the right track. There's 4 examples here. I guess we just did magnesium and oxygen, so we don't have to do that one. So lithium fluoride and fluorine, calcium and bromine, scandium and selenium. So let's look at this. I'm just going to do a couple of these really quickly in one note, and then we'll move on, just so we kind of maybe see a few more examples. Lithium and fluorine. All right, so lithium and fluorine. Lithium's Li, fluorine is F. Lithium on the periodic table is element number 3, and it has a charge of +1. It just says plus on your periodic table, but it's 1. So here's lithium. And then fluorine, it's over here on this side, and it has a charge of -1, although it just says minus, which is okay. So that's -1. Now, if you just think about it in your head, lithium has a charge of +1, fluorine has a charge of -1. Are they balanced? Well, yeah, they are balanced. If you want to think about it as the kind of crisscross method, you can bring that 1 down here, and you can bring that 1 down here. So you get Li with a 1 and F with a 1. But we don't write in the 1s. We don't need them. Just like exponents, if I had something like x to the power of 1, I wouldn't write in that exponent of 1. So just like in math, we don't use the 1s as exponents. So that's Li and F. And we would call that lithium. And then instead of it being fluorine, we change the ending of the nonmetal to ide. So it's lithium fluoride. So yeah, it's just LiF. That's it. Lithium. And instead of fluorine, we change the ending to fluoride. So that's one. I had a couple others. Let's do calcium and bromine. Calcium is Ca, bromine is Br. Calcium on the periodic table, let's find it. One thing about the periodic table is you'll see that they use the same elements over and over again in most of the questions, so it's really helpful to know where they are. So when I'm up here finding these things, it's important that you're looking for them too. It'll help you become good on like tests. You'll be nice and quick being able to find them. So you should have a general idea of where most things are on the periodic table. Some things are tricky to find. That's okay. You mean there's 100 and something elements, 118. It can be hard to locate some of these things if you don't use them all the time. But things in the first row, second row, and then basically all of the nonmetals, you should know exactly where they are. I'm not telling you to memorize it. I'm just saying with practice, you'll understand where they are as long as you're practicing, not just taking my word for it. So we had calcium and we had bromine. So calcium's +2, bromine's -1. Go back here. So calcium has a charge of +2, bromine is -1. Now, I'm going to rewrite both these things, CaBr, put them next to each other because they're going to form a compound. Two ways to think about it. I have to have my charges balance out. Calcium has a charge of +2, bromine has a charge of -1. How many bromines am I going to need to balance out the calcium? This is one way to look at it. So I'm going to need 2 bromines to balance out the 1 calcium. Or you can think about it as a crisscross of your charges. The 2 comes down next to the bromine, and the 1 comes down next to the calcium. So it kind of looks like this, Ca1, Br2. One super common mistake I see students make is they'll bring the charges down with them. Notice I'm not writing +2 down here or -1 down here. I'm just writing the numbers. So Ca1, Br2. Because I'm not talking about charges anymore, I'm talking about ratios of elements. And of course, we don't need to write in our 1s because they are assumed to be there. If I have the Ca, I know there's one of them. If I have more than one, I need to show that. So this is calcium, and bromine changes to bromide. So this is calcium bromide. There was one more example that I wanted to do. Scandium and selenium. This might be trickier. Scandium. Scandium is right here. So there's scandium. And selenium is right there. So scandium is +3, selenium is -2. See if you can do scandium and selenium and come up with the correct name for that. So write down the symbols, write their charges up next to them. You can think about crisscrossing them if you want, or you can think in your head, okay, I need to balance charges here. All right, so if I'm thinking crisscrossing of charges, the 2 comes down next to the scandium, and the 3 goes next to the selenium. Or you can think about it this way. Just write a little line here. Scandium has a charge of +3. How many scandiums do I have? I have 2 of them. Okay, what about selenium? Selenium had a charge of -2, and I've written down that I have 3 of them, so let's write in 3. What is the total of positive charges here? +3 and +3 gives me +6. The total of negative charges here is -6. They have to balance each other out. If they don't balance each other out, you've done something wrong. So that is how these work 100% of the time. If your positives and your negatives don't balance one another, then you need to go back and look at it again. The other thing is it needs to be in lowest terms. Last thing I need to do is write the name of this. I write the metal first, scandium. And this selenium changes to selenide. We always change the ending to "ide." Even though it kind of sounds funny, that's how we do it. So scandium selenium is actually called scandium selenide. All right, so there's 3 examples. Anybody have any questions about any of that? All straightforward enough? Maybe? Maybe not. All right, nobody's asking questions. You're maybe asleep. Maybe not. Did we do this? Magnesium, phosphorus. Yeah, we did. Manganese phosphide, calcium, oxygen. That was the tricky one. Name ionic compounds. We're good to go. Now, on your learning guide, page 20, there's a couple tables. Ava, you're good with that? That's good. Examples on page 20. So you've gone through these notes now up to here. No, up to here. And then on page 20, jumping down to the bottom, there are some examples. There we go. So determine the formula for the metal, the symbols, the charges, and then the formula for it. And then writing the name down below. I think I'm good for doing some work here. I've shown you a few examples. I think we'll take a little break here maybe. We'll maybe take a few breaks today. I don't know, maybe like formula each of the following polyatomics. Yeah, so you should be able to do this page, questions 2 and 3. Only page 20 though. You don't have to go on to page 21. So there's 2 questions, 2 and 3. There's a few parts to each one. Maybe give you like 10 minutes to go through that. If you want to take a break or whatnot, give your brain a rest. Make sure you get up and move around a little bit. But I would like you to go through these. If you have some questions, I will go through them with you after the 10 minutes. But I just want you to have a go at them. Again, it's super important that you guys start getting familiar with the periodic table, start using it, start looking for things. And one thing that I will mention is that if you're looking for something on the periodic table and you can't find it, like hafnium, like what is that? Hafnium? Never heard of that before. Is that even an element? Is that a typo? It's an element, hafnium. You look and look and you look and you look and you can't find it. You don't know where it is. There's one kind of way to kind of speed things up a little bit, and that is if you go to your data booklet. I'll just download a new one here. If you go to your data booklet you can see that you have the periodic tables on page 2, and then page 4 is an alphabetical listing of your elements. So you search for hafnium, you can't find it. Search for it, no idea where it is. Wow, this is taking a long time. Is there an easier way? Sure. You just go to the alphabetical listing and you're looking for hafnium. And here it is, hafnium. Symbols HF, element number 72. So what you can do is then go back to the periodic table and you know it's element 72. So right here, right in the heart of the periodic table, there's hafnium 72. That's a way to speed things up. And if you're running into issues finding things until you're kind of really good at it, use the alphabetical listing, and then you can go back. Sure, Taylor, I'll do the first one for you guys, and then I'll give you 10 minutes to do the rest. All right, lithium. The metal is listed first, and Li is lithium, and lithium's in the first column, so it has a charge of +1. Selenium, we just did Se, and it has a charge of -2. So if you want to think about crisscrossing the charges, you can do it that way. Or if you want to just think about balancing, well, lithium only has a charge of +1, whereas selenium has a charge of -2. So I need 2 lithiums, each being a charge of +1, to balance out the selenium that has a charge of -2. And if you think about crossing the charges, the 1 is going down next to the selenium, and the 2 is coming down next to lithium. So Li2Se is what you're doing. The second part is just naming these things. So I have Li and F, so Li is lithium. And fluorine changes to fluoride. So we change the ending from fluorine to fluoride. So that's the idea there. Likely won't take you 10 minutes, but we're going to put up 10 minutes. My tummy is a little grumbly, so I'm going to grab a snack, and we'll come back, and we'll see how you guys did. So there you go, have at her, and we'll see you in a few minutes. All right, guys, welcome back. You want to give me a green check just so I know everything's working and I can make sure you're back with me? Or, hey there, how are you? That'd be good too. Perfect, thanks, Taylor. Thank you, Savannah, Andrew, Bell. Excellent. All right, while we were gone, I went through the first little table here just so we could make sure we're on the right track. Now, the first two were pretty straightforward, and then the last two were really tricky. So hopefully you didn't get caught in the trickery. I say it like trickery as if somebody set up the question to be, really challenging for you, but it's not really that way. It's just the way that the charge is kind of balanced out. So, it's not an intention of ours to kind of make it difficult on you. It's just that's the way it worked out in terms of charges. So Li2Se is the first one. We did that one. Calcium and arsenic. Calcium plus 2, arsenic minus 3, CaA3AS2. So you have that one. Hafnium and sulfur. This is getting back to the oxygen one that we did. Hafnium's plus 4 and sulfur's minus 2. So when I crisscross my charges, I get a 2 down here and I get a 4 down next to my sulfur. But a 2 and a 4 needs to be simplified. I need to put it in simplest form. So this is why I encourage you to think about the charges and balancing the charges, because it's a little bit easier in this example to think about the charges. If you're sulfur and you have a charge of minus 2 and you need to balance out hafnium at plus 4, we only need 2 sulfurs at each at a minus 2 to get minus 4 to balance out the plus 4. So you're going to get HFS2. Aluminum, nitrogens, Al, and the 3 and the 3, again, you only need one of each of these things. If you crisscross, you're going to get Al3N3, and then you need to reduce that to lowest terms. So did anybody get caught on those last two? Because they are tricky with the reduction of the subscripts there. Other than that, I think you should be okay. Your dad runs a company called AL13. Aluminum 13? Sounds like a cool company. It's a cool name, at least. There you go. One other thing that kind of happens, you didn't simplify, Bell. That's okay. That's why we do practice. Does it have to do with chemistry? That's a good a question I should have asked. One thing that kind of happens from time to time, especially for something like this, ALN, students, when they write aluminum, write something like AL, like aluminum, and then the N. It's really important that we use the symbols that are on the periodic table for writing out these elements. Because if you have capital A, capital L, that means something different than A with a little l and then a capital N. And same thing with nitrogen. If you had big A, little l, little n, well, that's something completely different again than big A, little l, big N. So it gets confusing here in a second, and it's important that you use the symbols off the periodic table, exactly how they're written. Capital letter, lowercase letter. If there's two, you're gonna have capital, lowercase, capital, or you might just have two capitals. But capital letters, when we write compounds, indicate a new element. Hi guys, welcome back. If you wouldn't mind giving me a green check mark just so we can kind of make sure we're all in the right spot and we can hear the audio and everything's kind of peachy. Excellent. Good. All right, if anyone, well, I guess I can't tell anyone who it's not working for to give me a red X, but if you're running into issues or something crazy going on, just let me know in the chat. Cool. There is a problem with life size through all of the teachers in our building. So if it crashes a few more times, I wouldn't be surprised. I'll just keep, if you do run into issues, if it stops working, just type in chat so we can know. And then if we'll try to identify it and figure out how long it's going to take. So, all right, let's jump back to where we were. I did the first sort of table there, and then I asked you guys to name the following ones. Now, when we name these things, all you do is name the metal, then the non-metal, change the non-metal to "-ide". So lithium fluoride, calcium chloride, scandium sulfide, and rubidium oxide. No tricks, nothing crazy happening here. Just metal first, non-metal, change the ending to an "-ide". The one kind of way that we can trick you is sometimes we'll put you notice always have metal and non-metal. Sometimes when we just have a bunch of random ions around, you'll see the non-metal will come first. So you always want to put the metal first, then the non-metal second. And that'll just make everything a little bit easier. All right, so there's naming. I'm going to just kind of leave it at that unless anybody has any questions about that. We'll be moving on. Jump back into the notes. Okay, so we kind of take baby steps when we're doing this naming and making these compounds. So we've done those examples, we did that, we jumped through all of these little hoops here, got all that done. Naming ionic compounds, we talked about metal, non-metal, change the non-metal ending to "-ide". That's it, just that easy. Here's another example. Calcium, nitrogen. The subscripts don't matter when we're naming them. Calcium Ca3N2, doesn't matter. It's calcium, it's nitrogen, it's calcium nitride. That's it. It's kind of a gift when you see a nice, easy question. We did some examples. Now we're going to kind of take the next step to make things a little bit more complex, but just kind of introduce another kind of layer into the fray here. So when we say multivalent, what does multi mean? And what does valent mean? What do we associate those terms with? What does the word multivalent mean? Well, you guys probably know multi means many. You have a multivitamin, that's many vitamins. Multiple means many. It's kind of the root word, multi. So we have multiple and then valent. We talked about the valence shell, which is the same kind of root word as valence. So something that's multivalent has more than one outer electron configuration. And these are the guys in the periodic table that have all of these different charges. So manganese has 3 possible charges. There's a few others that have 3, but many of the multivalents will only have 2. So the way we have to distinguish these is we have to let you know, or you have to let me know, which charge we're dealing with. And the way we do that is with Roman numerals. So the example here is manganese sulfide. What is that going to look like? Manganese sulfide. Notice next to the manganese, I have the 3 here. And that means, hey, use the manganese with a charge of +3. That's what it's there for. Now, students often will start to kind of get a little bit confused between the ideas of adding these subscripts, and now we have these Roman numerals in here, which is a whole nother concept. So don't confuse the subscripts next to the elements with, don't confuse those subscripts next to the elements with the Roman numerals. They're different ideas. So Abby, I hope that'll be clear here in a second. All right, so manganese 3 sulfide. Manganese with a 3 next to it means manganese with a charge of +3. So when I write the symbol, manganese is Mn, and then I put the little +3 next to it. And then sulfur is always -2. So I don't have to worry about different charges for the sulfur. So that's kind of how we get that started. Now from this point, it's the exact same as what we were doing before. You can cross the charges down. So Mn, the 3 goes next to the sulfur has a 2, it goes next to the manganese. Or you can think about balancing the charges out. Whatever way it kind of works in your brain is the way that you should do it. So this is what it ends up looking like, Mn2S3. Now, Abby asked a really important question, and when we give you the name for the element, we will always tell you which charge we want you to use. You're going to run into problems when we're doing the backwards. So if I give you the compound, if you imagine everything on the slide was blank except this Mn2S3, and I asked you to name this thing, what's that called? Well, if you didn't know anything else, you kind of have to work backwards to figure out which charge is on the manganese. So if we give you the name, we say, hey, manganese 3 sulfide, the 3 tells you to use the charge 3. But if we're working backwards, you actually need to kind of figure it out yourself. So let's look a little bit at what that is going to look like here in a second. I'm just going to get out of the way here. These aren't in the notes, but the Roman numerals from 1 to 6 are over here on the side. If you don't know them, write them down right now, and that way you won't forget them. So 1 is I, 2 is II, 3 is III, 4 is IV, 5 is V, and 6 is VI. I do not recall any multivalents that have a charge greater than there's one that has a 7. I need to go one more. 7 is VII. So you need to add a 7 in there. I'm just kind of scanning through the periodic table, and I've noticed one with a charge of +4 and 7. So VII is 7. So that gives you the first few Roman numerals. You'll actually need to know them up to 10 once we start dealing with covalent compounds, but for now, that'll be a good start. All right, let's try this guy, Ti and F. Now notice it's capital T, little I, so the T and the I are together, and then the F is another element, fluorine. Ti is titanium. And when I go to my periodic table, titanium has 2 possible charges. Just glancing over, it could be +3 or it could be +4. How do I know which titanium I'm using? It doesn't tell me, and it doesn't need to tell me. But I can kind of work backwards to figure out what it is based on some other information I know. So I'm gonna let you guys, maybe if you're on the ball, you brought your A game to class today, you can think about it and tell me which titanium we're using. Maybe even use the Roman numeral, the 3 or the 4, to indicate which one. And then we'll kind of take a poll here and see what everyone's thinking, and we'll go through it. So which titanium? Titanium 3, titanium 4. You can vote in chat now. And then if you really think you got it, maybe you can kind of explain your thinking. You don't have to. If you just want to put in a 3 or a 4, that's great. But if you can kind of explain how you came to that, that would be really great. I got a vote for a titanium 4. I like it. Taylor's going with 4 as well. So we have 2 votes for 4, and that's it. Now, if you're really feeling brave, maybe you can explain why it's the 4. You guys are all right, so 4 is the correct answer, but why? There's lots of different ways to think about it. So yeah, if you got this far, I'm sure you're doing okay and you've got it sorted out. I'll put up the textbook definition here, and then maybe we'll see if you guys are on the same. I think on the screen it says titanium 4 because it's the one that balances the charges. On the screen it says titanium 4. Well, the 4 is next to the fluorine, not the titanium. So that's the one that balances the charges. And Abby, what you haven't written in that statement is that it's kind of implied, which is right, is that the fluorine always has the same charge. Fluorine is always -1. Always. Fluorine never has more than one charge. Titanium, it can have 2 charges, but fluorine is always -1. So if you have 4 fluorines and each of those has a charge of -1, that's a charge of -4. So if your charges need to balance and fluorine has a charge of -4, the titanium has to balance it out and it has to be +4. Or you can think about crisscrossing but working your way backwards. So taking the 4 from the fluorine and putting it back up next to the titanium, or taking the 1 from the titanium, putting it back up next to the fluorine. Does that work? So there's some really kind of straightforward ones here. And you can run into really complex ones. You can run into things with 2s and 4s, and you have to simplify, and they can get a bit tricky. I kind of like this stuff. I find it kind of fun because it's using some logic and some reasoning and trying to work backwards. I think it's interesting. So titanium is in fact 4 here because the charges need to balance out. Do I have one more? Nope. When we name it, we name the metal, so titanium, and then before we write the name of the nonmetal with the ending changed to "-ide", we have to put in the Roman numeral. So the Roman numerals only go in the names. They don't go in with the symbols. They go in the names. So titanium IV fluoride in brackets is titanium 4 fluoride. Or titanium, use the charge 4, and then fluorine gets changed to fluoride. So the naming structure is the same when we deal with multivalent metals. You name the metal, then you change the ending of the nonmetal to "-ide". The only difference that we didn't have before is that Roman numeral. So we have to put in which one we're dealing with. So in this case, it's 4. That's it. No more examples. Devastating. I want to look at some more examples. I'm trying to think where I have more examples. Maybe the learning guide has more examples. Let's take a peek. Determine the formula, polyatomic ions, brackets, only if they're needed. All right, scratch that. Let's go back to the notes. I don't want to carry on. Let's do a couple examples just on a blank sheet of paper before we move on, because I want to kind of draw a little break in your mind. I don't want to rush into the polyatomics. So let's, because the naming is often harder, I'm going to write down a few examples and then you can just name them. You can name them right into chat if you want. Let's pick one that we haven't done before. So let's go with V. And 3, no, P5. What is that one called? Mu. Mop. There you go. There's another one. Iron happens all the time. Iron is Fe. Let's go with FeO and Fe2O3. Those are both different. Let's pick one more. Let's pick a tricky one. Ru. O2. All right, there we go. 5 examples. What are they called? Now, some of them are kind of really easy to think about, and some of them get a little trickier, and I included a couple tricky ones in there. So the first one, V3P5. What are we calling that one? Vanadium phosphoride. Phosphide. Yeah, you guys are both on the right track. So phosphorus is P, and phosphorus always has a charge of -3. And if I uncrisscross the charges, the 5 would go up here, and the 3 would go up there, and we'd end up with, as you guys wrote it, vanadium. It's phosphorus, and we usually change the ending just to phosphide. So phosphoride sounds right, but we we like to have a kind of what am I looking for? A two-syllable sort of ending, phosphide, oxide, instead of phosphoride. Just kind of a finicky chemistry thing. MOP. MO is molybdenum. Oh, I forgot the Roman numeral here. The whole point of this thing. Vanadium 5 phosphide. All right, the next one, MOP. MO is molybdenum. I'll write it up on top here. MO, make sure I spell this right. LYBDEUM. Molybdenum. I'm going to have some sort of Roman numeral here because it has more than one charge. And then P we know is phosphide again. So which molybdenum? We've got a vote for 2 and we've got a vote for 3. When we are kind of confused, it's important to look at the nonmetal. So in this case, phosphorus always, 100% of the time, has a charge of -3. If phosphorus has a charge of -3, what charge does the molybdenum have to have? There's only one of them. I haven't written in a 1, but I know there to only be one there. What charge does it have to balance it out? It must have a charge of +3. Because if it had to charge anything else, the charges wouldn't balance. So molybdenum, in this case, has a charge of 3. Molybdenum 3 phosphide. So we need to be careful there. FeO and Fe2O3. Iron and iron oxide, iron oxide comes up a bunch. It's a popular one. Iron's a really popular metal, bonds with lots of things. We use lots in our everyday life. Iron is there. We have something and then oxide, and we have iron and oxide. What's the difference between those? We have a vote for iron 2 oxide for the first one. And then what about the second one? Hopefully you can kind of see how these two are different, the first one and the second one. Notice in the first one, I only have 1s next to each of these things. Now, always look to the nonmetal. The oxygen always has a charge of -2. So in this case, I have 1 oxygen and 1 iron. This is going to be iron with a charge of 2 because that 2 is going to balance out the oxygen. That's always the same. So Taylor, you got that one. The next one, oxygen has a charge of -2. So how many oxygens do I have? Well, I have 3 of them. Oxygen, -2, -2, -2. To total that, I end up with -6. What about my iron? I have 2 irons. What charge does each of these irons have to have in order for this to have a charge of +6? Because these have to balance. So if I have 2 and they have to add up to +6, I need a +3 and I need a +3. That's going to give me +6. So this is iron 3 oxide. Good job, Anna. So there you go. So the key for these multivalent metals, the metals with more than one charge, is to look at the non-metal. How about this last one, RuO2? It's kind of a tricky one. Intentionally tricky. What do we think there? What is Ru? I think that's ruthenium. It is indeed. The ruthenium is going to have some sort of charge, and then we have oxide. We have a vote for ruthenium 2. So on the periodic table, ruthenium has to be either 3 or 4. And again, we always look to the non-metal. So oxygen is always -2. Together, these two minus 2's give me an overall charge of minus 4. Now, my ruthenium has to have the same overall charge, and there's only one of them. I didn't write in the one, but there's only one. So if you get really caught into the crisscross method and then you start uncrisscrossing things to name them, this is why the crisscross method lets you down sometimes. Because if you uncrisscross those charges, you see a 2 next to the ruthenium and you put ruthenium 2, and that isn't even one of the options. So in this case, to balance out the minus 4, the ruthenium has to have a plus 4. So this is going to be IV. So that's why we have to kind of think in terms of charges. The crisscross works 90% of the time, but in that other 10%, you're going to run into problems. So hopefully you won't run into problems. There's that. Do I want to keep going? Yes, I do. Okay. That's multivalence. They'll pop up from time to time. The tricky bit here is that I'm going to introduce one more type of ionic compound called polyatomics. And then I'm going to give you guys some time to work. Now, when each of the things is by itself, if we just have like a regular ionic compound, metal, non-metal, no charges, nothing fancy, it's really easy to identify. If I give you something a little trickier with a multivalent, well, you have to put in the Roman numeral, but it's still pretty straightforward. We're going to crank it up another notch and talk about something called polyatomic ions. The problem comes when we put all of them together. So on a test or in some of the examples we're going to look at, it doesn't tell you which one's which. You need to be able to identify what type of ionic compound you're dealing with, and then the rules for naming it change a little bit. So I'll show you what I mean here in a second. Polyatomic. If we think about the word multivalent, we have multiple valent shells. Poly. Do you guys remember what poly means? Like a polygon? What did we talk about in Math 10 that was poly? I think polygons. Polyatomic and then ion. So if I had to translate that word from science into English, what would polyatomic ion? If you had to explain it to somebody who was 5, your little brother, your little sister, how would you explain what a polyatomic ion is? Poly means many. Atoms is atomic, so many atoms. And then ion is something with a charge. So a polyatomic ion is many atoms together that have a charge. What do you think? Could we handle that? Makes sense? Maybe a little bit? Well, when you put it that way, yes, it makes sense. All right, so these are groups of atoms that kind of bond covalently. We don't even really know what that means yet, but they join covalently, and they're really happy to live together, and they just have an overall charge. So instead of having something just like sodium, Na, that's always sodium, it's just Na. It's happy that way. We're going to have a group of atoms together. So sodium always has a charge of +1. If we have something like CO3, so the example here is CO3, the C and the O are both capital letters. They're together, and this group CO3 kind of lives life as a group. The C and 3 O's, they live together, and they have an overall charge. So these are what we call polyatomics. So polyatomics can be easily identified because as soon as you run into something with a polyatomic ion in it, you're going to see at least 3 capital letters, possibly more. What I mean by that is look at sodium carbonate here. We have sodium has the N, capital N, so that's one element. The C also capital, and the O is also capital. So this isn't NaCO, sodium cobalt, because we can't have sodium and cobalt together as 2 metals. So it's sodium, carbon, and oxygen. There are very, very few compounds, only one in fact, that will have the polyatomic at the beginning, having the beginning or the start of the element. Almost all of the polyatomics you're going to deal with are going to be at the end. They're going to act like nonmetals. So we'll look at them here in a second. So what is the formula for sodium sulfate? Now before we get there, what I want to do is, I'm just going to jump forward and then jump back. So on your data booklet, data page number 5, this is kind of a really small version of it because of just how it's formatted, but on page 5, you have a list and it's names and formula and charges of some polyatomic ions. So this table is super duper important, page 5 of your periodic table. So as soon as you see some sort of compound with more than 2 capital letters, a little light bulb should go off in your brain, a little blink, blink, blink. That's a polyatomic ion I'm dealing with. No other time will we deal with 3 capital letters. As soon as you see 3 capital letters, polyatomic ion, you're going to look to the chart. So the first example we looked at there had CO3. So if you start scanning down the column and you see CO3 is right here, it's called chlorate. Sorry, carbonate. I'll get a bigger version of this in a second. So you have carbonate here. Carbonate is CO3, it hangs out, it always has a charge of -2. These are all the ones that are really common that you're going to run into. They're all included in this table. There won't be ever any other polyatomics that aren't in this table. So all of the ones you're ever going to deal with are in this table. And one thing to notice is in the positive ions, the ones that act like a metal, you only have one, NH4. And you remember that from the nitrogen cycle when we were talking about nitrogen cycling through its ammonium. And then we have all the rest act as nonmetals. They're all negative. All right, so let's go back. Now that you know where to find that stuff. Okay, so the example here is right. What is the formula for sodium sulfate? Now, given the name of it, what do you notice is different about how this looks compared to all of the other compounds we've written down so far? What is special about this name, sodium sulfate? So sodium, you guys know what that is. Sodium's Na. It's on your periodic table. What makes sulfate a little bit different? Is anybody kind of seeing what I'm trying to get at or kind of figured it out? What if I said, write down the formula for sodium sulfide, or calcium chloride, or magnesium sulfide? So we're talking about sulfur, which is right, and Taylor, you're on the right track. It is a polyatomic ion for sure, Anna, but how do you know? How do we know when to look on the polyatomic ion sheet, and how do we know when to look at the nonmetals? What makes sulfate different than anything we've talked about so far? Give you a second. Some of you are typing. It doesn't end in "ide." Yes, Anna, you brought your chemistry game today, Anna. Brilliant. Yeah, the ending is an "ide." So far we've dealt with everything that we've dealt with has had an ending of "ide." Chloride, fluoride, selenide, bromide, on and on. They all end in "ide." This one doesn't end in "ide." It ends in 8. So that should be another little blinking light going off in your head. The ending isn't "ide." It's an 8. So if you look at all the polyatomic ions on page 5, all of the negative ones in this table, acetate, carbonate, chlorate, chlorite, I-T-E, that's not "ide." Chromate, cyanide is a tricky one. It's the exception. Dichromate, carbonate, bicarbonate, bisulfate, sulfate, bisulfide. Bisulfide is kind of a tricky one. Chlorite, nitrate, nitrite, perchlorate, permanganate, phosphate, phosphite, sulfate, sulfite. There's a lot of 8s and ites. So as soon as you see an 8 or an ite, you know that it's going to be one of these polyatomics. So sodium, Na, has a charge of +1. Sulfate is SO4, not to be confused with sulfite, which is SO3 and has a different charge. So sulfate is SO4. All right, so we found them. We found their ion charges. Sodium's Na has a charge of +1. SO4, sulfate, has a charge of -2. How do I combine these things together? It's the exact same as what we were doing before. We cross the charges, just thinking about balancing the charges out, and we end up with Na2SO4 1. Now, the tricky bit here is that when we have a group, we have a polyatomic, we can't put a subscript in the middle of it. It has to be that group all the time. So what we do is we put it in brackets to show that it's a group. Now, if we're only dealing with one, like this example here, the 1 goes after the bracket. Imagine how confusing this would be if we didn't have this bracket here. This would say Na2SO4 1. It would look like there's 41 oxygens if there's no bracket here. So what we do is we kind of drop the bracket and we drop the 1 if we're only dealing with 1. So down, we lose the 1, we lose the bracket. I'll just jump out of the way here. We have Na2SO4, no brackets, and that's what that guy looks like, Na2SO4. What happens if we have an example where we have more than one of the polyatomic ion? What is it going to look like in those cases? Well, let's do this example first, and then we'll look at a few extra examples. What is the name of the compound KClO? What are we going to call that? Now, this is the point where in your brain, little light bulb, oh no, I see more than 2 capital letters. I'm dealing with a polyatomic. Then you kind of need to think, is that a capital K, a capital C, a capital I, and a capital O? Or is that a capital K, a C, and an L, and an O? And what's together? Is the K and the CL together? Is the CL and the O together? It's all quite confusing until you get into a bunch of examples. Now the important thing, as I said before, is only one ammonium is going to begin your compound. So in this case, the K is potassium, and then the Cl and O, that's going to be something else. So the metal is potassium. We're never going to have these things start unless it's NH4 ammonium to start. So it's potassium. Now you need to find ClO on your common ion sheet. I think, Abby, you found it already. So we're looking for ClO. I'm going to find it. ClO. It's about midway down on that left column there. And Abby is right. It's called hypochlorite. So if we were to name this thing, we'd name our metal first, just like we always do. K, potassium. And then we call ClO hypochlorite. And the really cool thing about naming these things is we don't have to change the endings, because the ite is what makes it special. If we changed it to hypochloride, we'd get really confused. But this is hypochlorite. So this is potassium hypochlorite. The hint that I've written down here, we wrote it down already in your notes, but when you're dealing with polyatomics, you're always going to see 3 capital letters. And generally speaking, if you're not starting with NH4, the metal will be first by itself, and then you'll have the non-metal at the end. So that is super important. So there's your list. What I should mention is there's a few in the middle here, like HCO3. They have 2 names. So you can see these ones are separated with a comma. It says hydrogen carbonate or bicarbonate, hydrogen sulfate, bisulfate, hydrogen sulfide, bisulfide, hydrogen sulfate, bisulfite. You can pick either name. So you can pick the bisulfide or you can pick the hydrogen sulfide. Basically, the second one, bicarbonate, is its common name, and then this is its sort of chemical name, hydrogen carbonate, hydrogen sulfate's its chemical name, bisulfate's its common name. And you'll see that a few times, something like methane gas. We call it methane, but it's CH3. It's just some of these things come up so often that they have a common name. That's right, Taylor. When it's a polyatomic, you don't look to the periodic table. You look to the page 5. And one thing that it'll get kind of confusing because some of these names are really similar to some of the names you'll see on the periodic table, like chlorite and chlorate is really similar to chloride. And those things have Cl's in them. They have that chlorine ion in them, but they're bonded with the oxygen. Same with carbonate and carbonite and carbide. I don't want to do covalent compounds right now because I don't think we're ready for that quite yet. I don't want to confuse us any further. The notes aren't great because they kind of rush through this stuff, and you want to make sure we spend some time on it. Anna, great question. On a test, you'd get either one right. Yeah, exactly. You could write down either one. I guess the problem you can run into is on a provincial exam, they could put either one, and you'd have to kind of recognize that both are there, or you'd have to recognize that you could have either one. So, you know, if it's something like sodium sodium bicarbonate, it would be like NaHCO3, which could be sodium bicarbonate, or it could be sodium hydrogen carbonate. So if there's a multiple choice answer, you have to make sure you look for both of them. Taylor, what should we work on? I know, great question. What you should work on is this. In the learning guide, there are some questions. There are determine the formula for each of the following. You notice that these have polyatomics. So we have some bicarbonate, sulfate, phosphite. These aren't ides anymore. So as soon as you see 8 ites, you know you're talking about polyatomics. Now, I would suggest that in the learning guide, they include the absolute bare minimum that will allow you to have a most fundamentally basic understanding of naming and writing these compounds. I don't love the learning guide for Unit 4. So if you go through the learning guide and you rattle these all off and you do a great job of them, that's terrific, but you have only scratched the surface. So what I've done is this. Now, I know there's generally lots of work, and we've been, going pretty steadily so far, but haven't had a ton of work in this chemistry unit yet. So what I've done is this. If you were in my class, if I were teaching at a high school, I would probably do about 6 times as much work that's in the learning guide, and I would take more time to do it. So in Unit 4, I've added some supplemental sheets. I've called it Naming Extra Practice. Now, once you open it up, it starts with Lewis diagrams, which this is kind of a review of atomic numbers and energy levels and valence electrons and all that stuff that we did at the very beginning. Asks you to fill in the missing Lewis dot structures. Bohr diagram and Lewis structure, so you can see the similarities between those. And then I get into some of the naming stuff. So this is 18 pages of naming. Now, I know some of you are going to do it all and kill yourselves doing it, and I think that's amazing. But what I will say is that I've included a bunch of extra pages of practice, and I think that it's important that you do some of them. Now, you can see some of them are ask you for the name and the formula, zinc, bromine. I mean, these things don't take a lot of time. Zinc, Zn, bromine, Br -1, zinc +2, crisscross, boom, zinc bromide is the formula or the name for it. They're pretty straightforward. Then the next section here is naming multivalents. So these are things that have more than one charge. So you go through it. Chromium 3 phosphorus is chromium phosphide is the name. You have the 3 and the P. There you go. So you can do these, write the names and formulas. You should be able to do those fine. Then it's working your way backwards. If I give you the chemical formula, can you write the ion charge for the manganese? And can you write the name of this? And then it gets into this table where it's like ionic, covalent, or polyatomic. You have to figure out, is it ionic, covalent, or polyatomic? We haven't done covalent yet, so if you don't recognize something, it's likely covalent. Does the metal have one charge, monovalent or multivalent? And then what is the charge used? What's the name of the thing? Now, some of you are like, Mr. Bourne, do we have to hand this in? Is it important that we do it? It's just a lot. I'm not going to say do all 18 pages of it. If you want to, have a really excellent understanding of this stuff, I would encourage you to go through as much of this as you can. I'm not saying do it all. I'm saying go through it, kind of wrap your head around it. I'm going to spend some time going through this supplemental stuff next day. So once we talk about covalence, I want you guys to spend some time going back and looking at naming this stuff. Now, in a regular classroom, I would have a test at the end of naming, but the way the course is kind of worked out, you guys only have a test after naming and balancing, which are two huge units in my opinion. And if you move on to chemistry in grade 11, the naming that we're doing now is so important for everything you do in chemistry 11. So if you have any aspiration of moving on into chemistry in grade 11, then you definitely should go through all of this stuff just to make sure you have a really strong handle on it. Now, it's a lot. I don't want you to do it all for next day. What I want you to do is maybe work on a bit of it here and there. I'm not going to collect it, but I will go through some of it in class. The learning guide I will collect. So just like always, all the stuff that's in the learning guide is important that you go through, but the learning guide is an absolute bare minimum that will just get you a passing mark on this section on your provincial exam. There is so many different variations of these, the elements being combined together that can, make your head spin. So it's important to kind of understand them all individually. So to answer your questions, no, there is no project or assignment for chapter 4. What I want you guys to do is the extra practice we have, I've included here. So go through some of it. The more you do, the better. The less you do, not a good plan. But do as much as you can. Don't kill yourself, but do some of it. The learning guide needs to be done for sure. So go through the learning guide for next day. I'll go through the answers. You should be up to page, what are we up to on the learning guide? Looks like we can do that. You should be up to page 23 on the learning guide. So that should be done for next day, which is going to be April. Today is the 4th, so April 6th, I'll see you guys again. So you should be up to the end of page 23 for April 6th. If you have questions on that stuff, I'll go through it. Once I go through covalent next day, I will do some questions on the extra supplemental stuff that I've added next day as well. And so we'll do just covalent and supplemental next day. And balancing will not be on the midterm. I'm thinking that's a good plan. So I didn't know at the beginning of class how far we get today. So some of you asked at the beginning, what's on the midterm? We're going to do chapters 1, 2, 3, and 10, which we've all gone through. And then we are going to do the first 2 sections of chapter 4. So naming, ionic and covalent, and then atomic theory. So protons, neutrons, electrons. Bohr model, Lewis dot. So that's it. The balancing chemical equations, which is section 4.3, we won't get to this week. We'll work on that next week. And that will not be on the midterm. So the midterm will cover units 1, 2, 3, and 10, and then the first 2 sections of Unit 4. Covalent we'll cover next day, so you can just skip anything that says covalent, and then we'll go from there. So I was going to continue on, but I want to stop there because if I introduce covalent now, it'll just confuse me and confuse you, and I don't want you guys to be confused. So go through the learning guide up to page 23. I mean, we had class scheduled for another 25 minutes, so I would encourage you guys to use that time. If you finish it real quick, you want to go through some of that supplemental stuff, go through it. I'll go through some of it next day in class with the covalents, and I'm going to leave it there for now. Does anybody have any questions before kind of sign off for today? I think we've probably covered most things we need to. So covalent is, I want to keep it separate in our brains because it's a whole nother thing in itself. No questions is a good thing. Perfect. So I'm going to leave it there. I will answer any questions you guys have next day on this stuff. I hope there's lots. And as I keep saying, please go through this. Don't just wait for next day and then see some more of it. It's just going to kind of build into this huge snowball until it's an avalanche and you're just caught in an avalanche. You don't want to be caught in an avalanche. You want to take it one snowflake at a time, and you'll be doing A-okay. It can get overwhelming. So there you go. I will see you guys next class, and come with questions, come with this stuff done, and I'll go through the answers with you. Thanks, guys.